Weak base equilibria and Kb. Calculating the pH and pOH for a weak base solution. Okay, so let's remind ourselves of strong versus weak bases now. Strong bases dissociate completely in solution to produce hydroxide. 100% dissolution, we indicate that with a single arrow. Weak bases only partially react in solution, and so we indicate this with a double arrow with an equilibrium arrow. And we have ammonia in water to produce ammonium, which is the conjugate acid, and hydroxide. Now let's also remind ourselves of the Bronsted-Lowry definition of a base. And these are compounds that accept protons, or H+. So again, we have ammonia in solution reacting with water. Water is acting as the acid. It's donating an H+, and ammonia is accepting it. And that forms ammonium and hydroxide. And so ammonia is accepting the proton from water and acting as a base, and ammonium is the conjugate acid for ammonia. Okay, so how do we calculate the pH of a weak base solution? Well, we do it very similarly to a weak acid solution. So we're going to use the fact that an equilibrium exists between the weak base and its products. And then we're going to use the equilibrium constant K and the initial concentration of a weak base in solution, just like we did for weak acids. So we're going to use an ice table. Reminding ourselves of the general format of a weak base in solution. So here's our weak base. They don't have to be charged, but they often are, reacting with water to produce hydroxide and the conjugate acid. And we're going to have an equilibrium constant expression, just like we did for the weak acid solution. So we're going to have products over reactants. We're going to remember that the activity for a pure water is 1. And we're going to rename our equilibrium constant Kb for K base. Okay, so that's the base dissociation constant. Kb is the base dissociation constant. And as an example value, Kb for nitrite is 2.2 times 10 to the negative 11. So if we write our equilibrium constant expression, Kb, products over reactants, and then we plug in that Kb value, we have something that we can use in an ice table. We have an equilibrium constant expression. Now, let's go ahead and calculate the pH for a weak base in solution. Now, this process requires an additional step from the weak acid solution. So we're still going to use, in this case, Kb, since we have a base, and we're going to use an ice table, and we're going to figure out hydroxide concentration at equilibrium. Now, we're going to use that to calculate pOH. We're not going to be able to calculate pH directly with that value, but we can use the pOH to calculate the pH very easily. And so let's go ahead and start by calculating the equilibrium concentration of hydroxide in solution so we can calculate pOH. So here's our example problem. We're going to start with a 0.25 molar nitrite solution, which is a weak base, and the Kb for nitrite is 2.2 times 10 to the negative 11, and we're going to calculate the pH. Again, the first step, write the chemical equation for the weak base equilibrium. These problems are always going to start this way. So let's take this nitrite and we're going to put it in water, and that's a weak base. It's going to produce hydroxide. So water is going to donate a proton. It's going to act as an acid to form nitrous acid, which is the conjugate acid, and hydroxide, which is the conjugate base of water acting as an acid. So again, put your weak base in water and generate the products. So you're going to have the conjugate acid and hydroxide. We are going to start an ice table. And so remember, initial, change, and equilibrium. Okay, so we set up our ice table. Next, we're going to plug in our initial conditions. So again, remember that 0.25 molar nitrite solution, that's our initial concentration of nitrite, and we are saying that there's no hydroxide and no conjugate acid or nitrous acid at the beginning of this reaction. Now, as this reaction approaches equilibrium, some of that nitrite is going to be used up, and we're going to make hydroxide and nitrous acid. So minus X, because we're going to lose some of the nitrite as the system approaches equilibrium. At equilibrium, we're going to add everything together. So we have 0.25 minus X for the nitrite solution, and then we have X for each hydroxide and nitrous acid. And the next thing we're going to do, similarly, and you should be becoming very comfortable with this at this point, you're going to write your equilibrium constant expression. You're going to plug in the numerator, so X times X, that's going to give us X squared. In the denominator, we're going to have the reactant, because remember, the activity of pure water is 1. So we're going to have 0.25 minus X in the denominator. We're going to set that equal to our Kb value because we have a base in solution. And we're going to solve for X. Now, here's another shortcut. It's the same one that we used for the weak acid solution. Because Ka is small, we're going to assume that this X is really small. And in fact, it is. And we're going to say that it's much smaller than 0.25. So in other words, very little of this is actually going to react. So this X, the amount used up, we can just assume it's essentially 0. And so we can plug in 0 for that. And so we're going to solve for this X. Now, another thing to keep in mind, I mentioned in the weak acid equilibrium problem, is that you could use the quadratic equation for this also. So if you're more comfortable with that, go ahead and do that. And so once we make our assumption that very little reacts, then we're going to end up with X squared over 0.25, which simplifies the calculation a lot. And now we're going to go ahead and start solving for X. So 0.25 times 2.2 times 10 to the negative 11, and that's equal to X squared. When we do that multiplication, we're going to end up with 5.5 times 10 to the negative 12. When we take the square root of both sides, then we're going to end up with 2.35 times 10 to the negative 6, and that's equal to X. And you can see that X is actually really small. That's a very small number. And also remember that this X is the hydroxide ion concentration. Okay, so now we're at the point where we're going to calculate the concentration of all of our species in solution. And remember, we don't really care that much about the nitrous acid concentration, which is just X. And we don't really care that much about the nitrite ion concentration either. And by the time you subtract off 2.35 times 10 to the negative 6 from 0.25, you get approximately 0.25 molar nitrite ion concentration also. Now the part that we do care about is this hydroxide ion concentration. And because it's the hydroxide ion concentration, remember, we can't calculate pH directly from that. But we can calculate pOH. And so if we plug in our hydroxide ion concentration into negative log of this hydroxide ion concentration, we're going to get 5.63 as the pOH. Now we still need the pH. We're not done yet. We have the pOH. And so let's remind ourselves of these relationships which make our life much easier. So pOH and pH, when you add them together, you get pKw. And at 25 degrees C, that's equal to 14. And so let's use this relationship to calculate the pH. So here's our equation. And then we have a pOH equal to 5.63. Going to plug that in and end up with a pH equal to 8.37. And that is a basic solution. So the pH is greater than 7. Now, one way you can catch yourself if you calculate the pOH and then label it the pH is if this were the pH, 5.63 would be an acidic solution, and we have a weak base in solution, so that doesn't make any sense. We shouldn't have an acidic solution with a weak base. So our pH should be greater than 7 at the end of this. Okay, next we're going to talk about conjugate acid-base pairs and the relationship between Ka, Kb, and Kw.